So, welcome to the final semester. Today we'll be talking about a couple of different topics. We'll start by briefly going over some more partial fractions, which we covered last week as well. Then we'll also talk about how to find the area between two curves and some volume by revolution. Those are just a couple of different applications of integrals. So let's start with partial fractions. And if you recall, if we wanted to take a term and split it up into partial fractions, there are a couple of situations that are a little more complicated than normal. So I'm going to talk about what to do if you have some repeated factors. And what I mean by that is, let's say, we'll do an example. Let's say you've got the term 1 over x times x minus 1 squared. In this case, since you've got a squared term right here, this is a repeated factor, since you have two of those. So we actually have to decompose this into a over x plus b over x minus 1 plus c over x minus 1 squared. And the reason you do this is because one of your factors could theoretically be with just one x minus 1, and another could be with x minus 1 squared. So you need to account for both of those potential factors. And if we wanted to continue solving this partial fraction equation, well, we could write that 1, the numerator of the left-hand side, is equal to a. To get a over x to have the common denominator, we need to multiply by x minus 1 squared on top and bottom. Since we're only looking at the numerator, though, we just have a times x minus 1 squared. And for b, we need to multiply by x and x minus 1. And for c, we just need to multiply by x. Now, we can just plug in values for x. So we'll start by letting x equal to 0. Then 1 is equal to a times negative 1 squared. So a is equal to 1. Next, we'll go ahead and let x equal to positive 1. Then positive 1 is equal to 0a plus 0b plus c. So c is equal to 1 as well. Lastly, we have a couple of different options to solve for b. We could either plug in another value for x that's not 0 or 1 and solve for b. Alternatively, we could look at just the terms that have an x squared in it. For instance, on the left-hand side, there are no terms with an x squared in it. So we'll put 0 equals. On the right-hand side, a times x minus 1 squared, if we distributed x minus 1 squared, that would give us x squared minus 2x plus 1. Well, we only care about the x squared term. And since a is equal to 1, we have a times x squared is x squared. Here we have b times x gives us bx squared. Then that would be a minus bx, but since it's not an x squared term, we don't care. And again, c times x doesn't have an x squared term. Then we simply need to solve this equation right here to make it true for all x values. And it's easy enough to see that if we have x squared minus x squared, that's equal to 0. So b should be equal to negative 1. So that then tells us that our answer should be 1 over x minus 1 over x minus 1 plus 1 over x minus 1 squared. Make sense? All right then. So that is when you have repeated factors. You just need to make sure you account for all the factors that includes the lower powers of these factors. Another complicated situation you might run into with partial fractions is if you have factors of higher degree. So, for instance, if on the denominator you had a quadratic that you couldn't factor, such as x squared plus 1, then that's another complication because you can't have just a constant as the numerator. So we'll go ahead and do another example. Let's say you wanted to decompose 1 over x times x squared plus 1. Well, in this case, the decomposition would be something over x plus, in this case, our second term should be x squared plus 1 because we can't factor this. But then in the numerator, we actually need bx plus c because we want the numerator to have a term that is, I believe, 1 degree lower than that of the denominator. So you can see with a over x, the x is a polynomial of degree 1. So a, which is a constant, should be a polynomial of degree 0. Here, x squared plus 1 is of degree 2, so bx plus c would be of degree 1. All right. So if we went ahead and solved this out, the numerator on the left is 1. So that should be equal to a times x squared plus 1 plus bx plus c times x. And then, again, we can just plug in values for x. We'll start by letting x equal to 0. Then 1 is equal to a plus 0 times bx plus c. So a is equal to 1. Next, next we'll actually look at just the x squared terms. So if we rewrote this, 1 equals ax squared plus a plus bx squared plus bx. If we looked at just the x squared terms, then 0 equals to a plus b, since a is equal to 1, b is equal to negative 1. Next, we can look at just the x terms, and this is the only term with an x in it, so we can write 0 equals to b. Sorry, that should be a c right there. That's what I'm stuck. There we go. Cx, bx squared, and then c distributed to x. So c is equal to 0. Then our answer would then be 1 over x minus x over x squared plus 1. Make sense? Any questions? Cool. In that case, let's go ahead and do, could you see the problem again? Would you like it worked out from the start? Or is there like a specific part that's confusing you? Just the original problem? Okay, you're welcome. Let's go ahead and do a couple of practice problems with these now. Just go ahead and try many of these as you like. And see 4x plus 3 over minus 3 squared times x plus 1. That'll be the first one. Do a second one. 2x over. All right, I'll give you guys a couple of minutes to try those out. Good luck. All right, how's it coming? A, you found that C is equal to 15 over 4. Okay, good. And you found B is equal to negative 1 over 16. Okay. All right. Cool, cool. Let's go ahead and work through A. Just going to erase B for now. Well, first off, we need to figure out what this decomposes into. Of course, your A, B, and C will change depending on what order you put them in. In this case, I'm going to put my single factor x plus 1 first. Then we have b over x minus 3, but since x minus 3 is a repeated factor, we need to have it squared as well. Then we let our numerator, 4x plus 3, equal to this opposite side. We've got a times x minus 3 squared plus b times x plus 1 times x minus 3 plus c times x minus x plus 1. There we go. All right. Then we just pick values for x. We'll start by letting x equal to 3. Then 4 times 3 is 12, plus 3 is 15. 0a, 0b, so 4c. So c is 15 over 4. Next, we'll go ahead and let x equal to negative 1. Then negative 1, since we plug in negative 1 into 4x plus 3 and we get negative 1, equals to a times negative 4 squared. So that gives us 16a plus 0b plus 0c. So a is negative 1 over 16. Lastly, let's go ahead and look at just the squared terms. Our numerator has no squared terms, so we let 0 be the left-hand side. Then we have in our first term, a times x minus 3 squared will give us just 1 x minus 3. So that would be a, since a is negative 1/16. We can go ahead and put negative 1 over 16 there. B, we have x plus 1 times x minus 3, which again results in just 1x squared times b, so plus b right there. And then c has no x squared terms. So this equation is pretty simple to solve. B equals to positive 1 over 16. So then our final answer would be negative 1 over 16 times 1 over x plus 1 plus 1 over 16 times 1 over x minus 3, and I'm just writing it this way so we can more easily see the coefficients. And lastly, plus 15 fourths times 1 over x minus 3 squared. Make sense? Cool, cool. Did anyone get part B? Or the second one? That's all right. For time's sake, let's just go ahead and work through that now. To a new section of the whiteboard. The second one was 2x divided by x squared plus 3 times x minus 1. And again, we first need to set up our partial fraction equation. I'm going to let be a over x minus 1 plus, since our second term is of degree 2, that tells us we need bx plus c on the top. So then 2x is equal to a times x squared plus 3 plus bx plus c times x minus 1. Let's start by letting x equal to positive 1. Then 2 is equal to 4a. So a is equal to 1/2. Next, let's look at the x squared terms. Left-hand side, we have no x squared terms. Right-hand side, we have ax squared, so 1/2 x squared plus bx squared. So that tells us that b is negative 1/2. And lastly, what we can do is we can actually look at the x terms. So 2x on the left-hand side. In this case, we might want to distribute this portion. I'll go ahead and rewrite that. That is bx squared minus bx plus cx minus c. So it's a lot easier to tell we have a minus bx plus cx. And since we've got minus negative 1/2 as b plus cx, well, then it's pretty easy to tell that 2 is equal to 1/2 x plus cx. Shouldn't have the x's, I was dividing these sides by x. So 1/2 plus c, so c is 3/2. And here we have all three of our coefficients. So then we can just write them into our partial fractions equation. And we get 1/2 times 1 over x minus 1 plus, then we have bx, so negative 1/2 x plus 3/2. That's our bx plus c times 1 over x squared plus 3. Any questions? Does that all make sense? Cool. All right then. Would you guys like to do one more partial fractions problem? Or should we move on to the next section? One more problem? All right. Let's see. Go ahead and try out this one. And I'll give you a few minutes to do that. Good luck. gotten a equals to negative 1 equals to 0, and c equals to 5. All right, I believe that's the correct answer. Let's go ahead and work this out. Let that be a over x plus bx plus c over x squared plus 4. Since we do have a term that isn't factorable into linear terms, so we've got a quadratic term as a denominator, we need bx plus c as the numerator. And 2 is equal to a times x squared plus 4 plus bx plus c times x. All right then, let's start by letting x equal to 0. Then 2 is equal to 4a, so a is equal to 1/2. Next, let's go ahead and look at the x squared terms. So b is equal to negative 1/2. Am I moving a bit too fast on this one? Just realized I might be going a tad fast. You're good so far? Okay. So I just collected the x squared terms. Ax squared bx squared. There. And then that tells us that b is equal to negative 1/2. Lastly, I'm going to collect the x terms. So that would be c times x right there. And there's none on the left-hand side. And we actually don't get any x terms from a times x squared plus 4. Over the bx squared instead of equal to 1/2. Right. Yeah. Another way that I sometimes think about it is, well, how many x squares would we just need to subtract? And well, clearly 1/2 x squared minus 1/2 x squared would get us 0. But yep. Do I sub in x is equal to 1 when I compare the x's? Kind of. Not really though. Let's see. So really the theory behind this is this equation, this 2 is equal to, this is the numerators essentially of both sides. This should be true for all x's. So no matter what x value you plugged in, it would still be true. And because of that, there's actually a theorem that says if you have like a polynomial and it's equal to another polynomial, then you can actually look at the terms that have the same degree, so the x squared terms, and say, well, their coefficients have to be the same. And that's kind of what I'm doing here, is I'm looking at the different terms of different degrees. So I find here are all the x squared terms, a times an x squared there, and then bx distribute to this x, gives me a bx squared. So then ax squared plus bx squared has to equal to the number of x squared terms on this side, which is like a 0x squared. And then you could theoretically just divide both sides by x squared, and you're getting an equation 0 equals a plus b. So that's kind of what I was doing. Does that make sense? Yeah, no problem. All right. So now we have found all of our coefficients, and you were exactly right. We have a equals to 1/2, b equals to negative 1/2, and c equals to 0. So our final answer would be 1/2 times 1 over x minus 1/2 x times 1 over x squared plus 4. Just like that. All right. let's go ahead and go on to next thing, which is the area between two curves. So let's say you had two functions. Call this one f of x. And let's say we also had just like a linear function. We'll call this one g of x. And you wanted to find this area between them right here. And the question is, how do you go about finding that area? Well, it's actually pretty simple, because it turns out it's just actually the integral, if this is A, the first intersection point, B is the second intersection point. This is actually just the integral from A up to B of f of x, your top function, minus your bottom function, g of x. And it's a lot easier to see this if you think of it in terms of just what the integral means, because an integral represents area. So this blue part is the integral from a to b of just g of x. Then hopefully you can see this green line. It's getting a bit too crowded, but regardless, all of that green part would be the integral from a to b of f of x. And you'll notice that it overlaps exactly in the red part, which is exactly the green part minus the blue part. So that's kind of a physical representation if you can sort out all the colors that are there. But it's really not too difficult to find the area between two curves. For example, if we wanted to find the area between y equals to x squared and y equals to x. First, we would want to draw a picture just to kind of see what's going on. Here's y equals to x squared. And I'll keep going like that. Here's y equals to x. And it's almost a good drawing. You'll notice that y equals to x is on top. So they also intersect at, we could find their intersection point by setting them equal to each other. And that tells us that either x is equal to 0 or it's equal to 1. So by our theorem, this area between them would be the integral from 0 to 1 of our top function, y equals to x, minus our bottom function, y equals to x squared. Then this is a pretty simple integral. The integral of x is 1/2 x squared, then minus 1/3 x cubed, evaluated from 0 up to 1, gives us 1/2 minus 1/3, which is equal to 1/6. So an easy enough process, right? Any questions about it? All right. I'm going to go ahead and give you a couple of practice problems. So go ahead and find the area of two functions. And we won't do that one yet. Go ahead and work that one out. I'll give you a few minutes to. know which function is above without drawing it? Well, you've got a few different options. You can always just plug in points. For instance, you could always start by figuring out where these two functions intersect by just setting them equal to each other. You've got that there. Then you would solve and say, okay, 0 equals to x squared plus 4x. That's x times x plus 4. So then it intersects at 0 and 4. And since it only has two intersections, you know that one's going to be above the other the whole time. So then you could just pick x equals to 2 and say, well, when I plug x equals to 2 into y equals minus x squared minus 2x, that gives me minus 4, so minus 8. And that's clearly smaller than y equals to 2 times 2, which is positive 4. And then you could say y equals to 2x is on top. Does that answer your question? Okay. You're welcome. I basically just picked it because I knew it was a number between the intersection points. So I could have picked 1 or 3 or 5 halves, basically anything as long as it was between 0 and 4. You're welcome. You got negative 32 minus 64 over 3. Okay. I think you might have switched a couple of terms around. Let's go ahead and work through this. So we already figured out that y equals to 2x is the top function, and we found out our intersection points as well. We wanted to sketch a graph of it. It's not a huge deal, but basically we've got y equals to 2x like this. We've got 64 over 3. All right. Again, our graph would look kind of something like this. Oh. All right. No, I think I'm wrong. This is a... Oh, that's what I did wrong. Aha. It intersects at 0 and negative 4. That's why. Because in order to make this equal to 0, you need a negative 4. So then we would need to choose a value between negative 4 and 0. And then we would be able to see that actually it's y equals to negative x squared minus 2x is on top. Okay, that's my bad. Yep, thanks. Appreciate it. Then our theorem tells us we're going to have the integral from one intersect to the other of the top function minus the bottom function. And that gets us negative x squared minus 4x dx. So negative 1/3 x cubed minus 2x squared from negative 4 up to 0. That gets us 0 minus negative 1/3 times negative 4 cubed gets us positive 64/3. Then negative 4 squared gets us 16 minus 2 times negative 2 gets us minus 32. That would be distribute the negative 32 minus 64/3, which is, let's see, I believe that is equal to exactly 32/3. Double check that really quick. Let me work that into a calculator. And we get 32/3. That's the final answer. Yeah, it's that's why drawing a picture can be helpful. If we actually could graph it, if we could graph it, we would see we have an intersection at 0 and at negative 4. So something like this. That's more what the region should look like. All right. There is one other tricky thing about finding the area between two graphs. I'm just going to do this one as an example. Let's say we wanted to find the area between y equals to sine x and y equals to positive 1/2, but on the region from 0 to 13 pi over 6. With this one, we're definitely going to start by drawing a graph. So sine of x looks something like this. And we actually need a bit more than a full phase because we're going all the way up to 13 pi over 6. And then we have the line y equals to positive 1/2. That's right there. Okay. So the big issue with this one is we've actually got 3 intersection points. So the area between these two graphs is actually this region right here, but it's also this region right here. Which means that halfway between, we actually need to change which function is the top function and which function is the bottom function. So on this region here, this would be from positive pi over 6 to positive 5 pi over 6 just by unit circle values. Sine of pi over 6 gives us 1/2. So does sine of 5 pi over 6. On this interval, sine of x is on top. So the area, this little part here, I'm going to call it region A, be the integral from pi over 6 to 5 pi over 6 of our top function, sine of x, minus 1/2 our bottom function. Then we've also got this other region, we're going to call it E, and it goes from 5 pi over 6 would that area also be included? Technically, the issue here is that it would be reversed. So let's see, this would be 1/2 minus sine of x. If we flipped the order around in this and kept it as sine of x minus 1/2, then this area would actually end up being negative what it's supposed to be. So part of b would actually cancel out a, and that's not what we want. That's why we need to split it up like this. Does that kind of make sense, or would you like me to explain a bit more? Oh, would that not be the area from... Oh, sorry, I think I maybe misread your question. That area from 0 to pi over 6. Well, the thing is, from 0 to pi over 6, this area here isn't actually completely enclosed. Right, like because we don't actually have the vertical axis as part of any of our bounds, so this isn't like a fully enclosed shape. If you wanted to be really pedantic, though, I'll just change the problem to pi over 6. Just to eliminate any confusion. Because this gets the point across just as well that there are some problems that you do need to flip the order around and change which function is on top partway through. But it was a good question. Yeah. And then our final answer would just be so plus b. Let's see. Yeah, we'll go ahead and integrate it. So the integral from pi over 6 to 5 pi over 6 of sine of x minus 1/2 would get us sine x minus x over 2 from pi over 6 to 5 pi over 6. And then we would add b, so plus x over 2. The integral of minus sine x is positive cosine x from 5 pi over 6 to 13 pi over 6. And that gets us, oh boy, plus root 3 over 2 minus 5 pi over 12 minus cosine of pi over 6 is negative root 3 over 2, then minus pi over 12. Boy. Then we have, I'm just plugging in all the values, plus 13 pi over 12 plus root 3 over 2, since cosine of 13 pi over 6 is the same as cosine of pi over 6, minus 5 pi over 12 plus, that would be minus root 3 over 2. And all we need to do is fully simplify. So here we got 3 over 2 plus root 3 over 2 minus That should be 5 pi over 12 minus pi over 2. So root 3 minus pi over 2. And then here we have 13 pi over 12 minus 5 pi over 12 gives us 8 pi over 12, which is 2 pi over 3. And then plus another root 3. So our answer is 2 root 3. That 2 pi over 3 is 4 pi over 6 minus 3 pi over 6 gets us plus pi over 6. And hopefully I did all the simplifications correctly. But if you're interested, that should be the final answer. Any questions? Then we'll move on to the last topic, which is going to be volume by revolution. And the big theory behind this one is, let's say you had some kind of shape. We're going to start with just a very basic line. And let's say you took that shape and you spun it around the x-axis so that it made a big ol' round thing. And I can't quite draw very well, so you'll have to do your best to imagine this is a perfectly drawn shape. But regardless, this would end up making a kind of cone like this. Hopefully you can see it. Where we basically revolve a shape around the x-axis. If you're interested, there are plenty of pictures you can look up. You might want to search for something called the washer method if you want a better visual for it, because I'm not great at drawing these. Regardless, let's say you wanted to calculate the volume of this shape. Well, actually, it turns out it's really not that difficult because it all comes down to the area of a circle. So let's say we actually took a cross-section of this cone. That would end up just being a circle because perpendicular cross-sections of a cone, the circles. And we're essentially looking at this from over here, this direction. And this is actually the height of our function at this specific point, the radius of our circle. So then the area of this circle is going to be pi times the radius squared. So pi times our value at that specific point squared would give us the area of the circle. Then if we actually integrate this value along these varying values of x, or along different radiuses of the circle, we can actually get to the volume of this shape. In other words, the volume of the shape would simply be the integral from wherever your starting point is to wherever your ending point is of pi times your function value squared. And you'll often see that written with the pi taken out front as a coefficient. So, for example, let's say someone had the shape y equals to negative x squared plus 4, and you're looking specifically on the interval from 0 to 2, and you wanted to rotate it about the x-axis. Then, by our theorem, all we need to do is take the integral from 0 to positive 2, got our pi out front, and then we just square that. and that would give us the volume. So we'll go ahead and work that out. And go ahead and distribute x squared gets us x to the fourth minus 8x squared plus 16. And then that gives us pi times 1/5 x to the fifth minus 8/3 x cubed plus 16x, 0 to 2. And that gets us pi times 32/5 minus, oh boy, 64/3 plus 32. And luckily I came prepared, and that simplifies down to 256 pi over 15. Any questions about this process? In that case, I'll go ahead and give you guys a practice problem. Let's see. Go ahead and try rotating secant of x on the interval from 0 to pi over 4. That should be a bracket about the x-axis. And good luck. Pi of tangent pi divided by 4 minus 0. All right. Let's go ahead and work this one out. So volume would be equal to pi times the integral from 0 up to pi over 4 of f of x, in this case secant of x squared. And that would be secant squared x. The integral of secant squared x is simply tangent of x. That would be from 0 up to pi over 4. So tangent of pi over 4 is 1, and tangent of 0 is 0. So we get pi times 1 minus 0. So our answer is, in fact, pi. Nice job. All right. We'll do, I think we can try out, yeah, we'll try out one more. See if you can figure out how to rotate y equals to 4 minus x squared about y equals to negative 5. And just on the interval from negative 3 up to positive 3. Go ahead and calculate that volume. It's not going to be quite the same process, but hopefully you can figure it out. Let's see. Rotate on about the line y equals to negative 5. So, for instance, if we had a picture, this here would be a line y equals to negative 5. We would have a quadratic like that. I'm saying rotate it right about that line there. Yeah. All right, anyone get an answer? That's all right. This one's a bit trickier, but it helps if you actually sketch out a picture. We are just about out of time, so I'm just going to go over this one and actually see what exactly the radius of your circle is. So this value r is actually the distance between y equals to -5 and y equals to 4 minus x squared. In other words, it's 4 minus x squared minus -5, which is 9 minus x squared. And since we're actually rotating around this y equals to -5 line, that r is the radius of our circle, which tells us that our volume should be pi times the integral of our area. Sorry, it would just be the integral of our area, which is pi times the integral of r squared. Does that make sense? Cool. So then, since we've already figured out what r is by using this picture to see exactly and visualize what our distance is, it's pretty easy to set up our integral from -3 up to +3, 9 minus x squared squared. So the volume is, there should be a pi out front, sorry, pi times the integral from -3 up to +3. Since it's even, I'm just going to double it and change it to the integral from 0 to 3. Then we would have 81 minus 18x squared plus x to the 4th. That gets us 2 pi times 81x minus 6x cubed plus x to the 5th over 5 from 0 to 3. And if we plugged in the values, we would get 2 pi times 81 times 3 is 243, minus 162 plus, oh boy, 243 over 5, I believe. Regardless, you can solve the arithmetic if you really care to. I'm just going to plug it in a calculator really quick. And we get 1296 pi over 5. Why was the line y equals to -5 not small r? In this case, it's because we are actually rotating around that line. If so, you're referring to a different kind of problem where, say, we have two functions like this, right? And let's say we wanted to rotate the shape between them like this, where this would be like a little r, this bottom function, and this top one would be a big R. Our volume would be pi times the integral of big R squared minus little r squared. You're asking why the line y equals to -5 wouldn't be the little r squared, correct? Yeah, so in this case, it's because it all comes down to essentially where your little representative rectangle is. So in this case, this isn't truly like a radius, because we actually need to account for essentially all this distance as well, because while it's not actually in our shape. Pushing it further out from this center will actually increase the volume. A better way to think about this second equation is it's actually taking a bigger shape and cutting a smaller shape out of it. For instance, it would be what happened if you rotated this top function around the x-axis and then cut out the shape of the smaller function rotated about the x-axis. Whereas in this instance here, we're actually rotating it around a different spot. So we need to actually say that this is a true radius. So in order to account for that, we don't need to subtract anything at all because our function extends all the way down to the axis that we're rotating it around. Does that make sense? Yeah, when I subtracted the 5, it was really to add it to the radius. Exactly right. Yeah, no problem. All right, I'm going to go ahead and stop.